Okay, this is Trig Sub. I'm not sure whether I just read the schedule wrong the first time or whether she changed it, but it looks like 7.3 in Trig Substitution is on your test, so I'll go ahead and make a couple of videos on it. If you've seen the videos on 7.2, which is trigonometric integrals, you realize that there are several techniques that we can use involving our trigonometric identity such that we can change the form of a given trig integral such that we can actually do something with it. Okay. Here in 7.3, we're actually going to take something like this, which involves no trig, and we're going to substitute trigonometry into the integral such that we can change the form and actually makes it much, much easier. Now you need to remember that trig integrals, trig identities are helpful because, especially the Pythagoreans, if you have 1 minus sine squared theta, if this was 1 minus sine squared theta instead of 1 minus x squared, you could actually change it from a from a binomial to a monomial. And that would actually help, right? Because the square root of cosine squared you can actually evaluate, and that would actually help things out immensely. That's kind of the logic behind this. You're introducing trig so that you can use your Pythagorean IDs to take radicands that are two terms and turn them into radicands that are one term such that you can evaluate them, and it actually cleans everything up really, really nicely. Now, these are a little bit long, these are a little bit burdensome, but let's go ahead and before I introduce the other ones, let's go ahead and work with this one. Now, what I'm going to do is I'm going to introduce the substitutionary relationship of x is equal to sine theta. Now, if I do that, obviously this radicand down here becomes 1 minus sine squared, which then turns into cosine squared, okay? But I have to remember that I have to substitute for everything else as well, okay? And that dx up there, that x squared up there is going to turn into sine squared. If I actually take this and differentiate it into the differentials, my dx is going to become cosine theta d theta, okay? Well, let's go ahead and work with that then, okay? Let's sort of pull it down here since I already sort of messed up going straight across. And we'll go ahead and change everything into theta. So I have sine squared theta, that's my x squared. We'll go ahead and pop the dx up here in the numerator. It's going to be cosine theta d theta. And down here, we're going to have 1 minus sine squared theta. Now that's going to turn into cosine squared theta, the square root of which is cosine, so that actually winds up crossing out like that, okay? Which means that I've changed this into a rather straightforward trig integral if I just remember what my power reducing formula is. And, you know, I happen to. 1 minus cosine 2 theta over 2, and of course the over 2 I'm just going to pull out in front as a coefficient. When I want to go ahead and turn this into two integrals, I'm going to change this coefficient into 1/4 because I'm going to need a 2d theta as my du. And now I have 1/2 theta minus 1/4 sine 2 theta plus c. Well, it's still in terms of theta. And that's going to be a little bit of a problem, especially since I can actually get sine theta is equal to x over 1, or theta is equal to arc sine of x over 1. But what about sine of 2 theta? Well, just double angle identity that bad boy, and you're going to wind up with 1/2 sine theta cosine theta plus c. Now, we can introduce this into the notation, but even easier is just to go ahead and draw the triangle, okay? If that's theta, then opposite over hypotenuse winds up being that, and this adjacent side, not surprisingly, becomes 1 minus x squared underneath the radical. Look familiar? It should, okay? So once I have this, I simply say, well, that's 1/2 arc sine x. There's really nothing you can do with that. But sine theta is x, and cosine theta winds up being adjacent over hypotenuse, right? Which is the square root of 1 minus x squared plus c. That right there is your integral. And what I had to do was I actually had to go ahead and pass through trig. Trig is basically, you're subbing in trig because it allows you to change the number of terms and resolve the radical such that you can then simplify and integrate and then substitute back in. Now, if you're curious whether this is indeed that integral, all you have to do is just differentiate that to show that you actually wind up getting back to that integrand right there. Okay? Well, that one was easy enough. Let's go ahead and move on to one that doesn't involve sine. Let's go ahead and look at one of the other trigonometric Pythagoreans and how that's going to help us with problems like x squared plus 4. Now here's the thing. If I'm going to be doing something like this, I want that to involve tangent squared theta plus 1 is equal to secant squared theta. Well, I notice that I have a 4 right here, so I don't want x squared to be tangent squared. I want x squared to be 4 tangent squared. And that, of course, results if I actually label x as 2 tangent. Because if I then substitute this in, I can factor out the 4, resolve the square root of 4 as a numerical factor, and I can pull it out in front unless it cancels with something else. From here, I can go ahead and do dx is equal to 2 secant squared theta d theta. And now I have all the pieces that I really need to change the form of this. Dx in the numerator becomes 2 secant squared theta d theta. 4 tangent squared theta down here in the denominator. 4 tangent squared theta plus 4. Okay, well that gets me a little ways along, okay? I know that this right here, once I've resolved it, is going to be 2 secant theta, okay? Factor out the 4, transform tangent squared plus 1 into secant squared, and underneath the radical I will have 4 secant squared theta, which square root it, that's 2 secant theta. At this point, I recognize the fact that that 2 can cancel with that 2. I recognize that one of these secants can cancel with this secant, okay? And then I'm left with, I'm going to go ahead and pull that 1/4 out in front. I'm left with secant theta d theta over tangent squared theta. Well, that looks like a mess. Except, you know, and I've taught you this before, when in doubt, let's change everything into sine and cosine. Secant is 1 over cosine. Tangent squared, if I'm dividing by it, is the same as multiplying by cotangent squared. Okay, well, this cosine cancels out with that cosine, and I'm left with 1/4, 1 over sine theta, cosine theta over sine theta d theta, and some of you may recognize that as cosecant theta, cotangent theta d theta. Well, in order for that integrand to be a recognizable derivative, I'm going to have to make it negative. And I have 1/4 cosecant theta plus c. Well, I'm not done because I have to transform it back in terms of x, but I'm certainly close, okay? Let's go ahead and take this relationship right here, transform it into tangent theta is equal to x over 2. That is going to help me draw my triangle, and I know that if that's theta, x over 2 is the opposite over the adjacent. That makes this x squared plus 4. Does that look familiar? It should, okay? And therefore I know that negative 1/4, now cosecant is the reciprocal of sine, so it's the hypotenuse over the adjacent, and I'm left with x squared plus 4 over x plus c. That right there is my integral. Now I'm probably not going to go through any definite integrals as I'm mowing through this. If you were doing definite integrals, you would just reintroduce the limits of integration from the original and basically scratch out the plus c and just evaluate the difference right there, okay? What I'm more interested in these particular videos is showing you the logic behind it, okay? So we've substituted in sine theta for an x expression. We've substituted in 2 tangent, or some coefficient times tangent in for x. Now the last one that we need to look at is substituting in secant. Okay, so let's go ahead and look at this next one. Let's look at dx over x squared minus 9. Well, again, I know that secant squared theta minus 1 is equal to tangent squared theta. That's going to be rather helpful. Now, I know that this is minus 9 and not minus 1, so I need the x squared not to be secant squared theta, but I need it to be 9 secant squared theta, so I can then factor out the 9. That means my actual substitution is x is equal to 3 secant theta. Okay, so I know what to plug in here for the x squared. I know what to plug in here for the x. The only thing left is to determine what I'm going to plug in for my dx up top. And so I just get the differential, and there are the 3 pieces of my substitution. Okay, this was just the identity that I needed to recognize in order to use it. So I know that the numerator, being dx, is going to be this expression in terms of theta. I recognize the fact that 3 secant theta times 9 secant squared theta minus 9. Well, this right here and this right here so obviously cancel out that you're just going to want to go ahead and do that. This is going to turn into 9 tangent squared theta underneath the radical, or 3 tangent theta. Okay? Well, that means that the tangents are going to cancel out. Okay, well, that's a little bit shocking, but let's go ahead and continue. I recognize the fact that that's going to be 1/3 d theta. And if I have 1/3 d theta, that turns into 1/3 theta plus c, or 1/3 arc secant x over 3 plus c. Oh my gosh, I should have been able to recognize that as arc secant right from the very beginning. Do you see it? Because remember that when we differentiate arc secant u, that winds up being du over u times u squared minus 1, which is exactly this form, just a little bit altered. I mean, it would be very easy to turn this into that form just by multiplying through by constants strategically, okay? This was a simple arc secant if you recognize the form. If you don't recognize the form, it winds up being rather straightforward. It's just not a whole lot of fun the other way. But notice that it didn't really take that many steps. Okay? Well, we've done 3 examples here that I've moved through rather straightforward. Okay? We'll go ahead and do a few more in the next one. But basically what we want to do is we just want to specify one last thing before we sort of sign off here. Okay? If you have a radical which is a squared minus x squared, where a is just any constant, you're going to want to substitute in sine theta, okay? Because you're going to be using the 1 minus sine squared theta is equal to cosine squared theta identity. Or more specifically, you're going to be using a squared minus a sine squared, a squared sine squared theta is equal to a squared cosine squared theta, which is of course the same thing, right? This is, if it's 1 minus x squared. This is if it's a minus x squared. But it's the same idea, okay? So if it's a squared minus x squared, very simply plug in sine. Okay, well what if it's x squared minus a squared? Well, at that point, I'm going to need it to be a secant theta because I know that I'm going to be using this identity, or more generally, a squared secant squared theta minus a squared is equal to a squared tangent squared theta. Okay, this is the identity. This is it more in a general form. You cannot take, you cannot take the radical of this. You can't actually execute that radical, but once you transform it, that's a monomial in the radicand, and you certainly can. That's, of course, the whole point behind all of this. Lastly, x squared plus a squared, we're going to be using the only addition form that's going to pop up in this particular section. And so I'm going to designate a as tangent theta because I want a squared tangent squared theta plus a squared to transform into a squared secant squared theta such that I can actually take the radical of it and therefore clean up the integrand, integrate, and then transform it by using my knowledge of trig back into the original variable. Okay, so this is basically what's going on. We'll do a couple more examples, maybe 1 or 2 more videos, and then we'll move on from there into what's either called the trapezoidal rule, or more generally is usually in sections called integration by approximation or numerical. For our purposes, it's, I think, 7.7, okay? Go ahead and be on the lookout for that. Again, email me with any questions that you might have. Bye.